which is going to be given by Pierre Lanari. And he's going to be discussing another very important topic, and that is the importance of reactive bulk composition, and also an approach called Bingo-Antidote that he and co-authors have developed.
Great, thank you very much, Dave. I guess you can see my screen now. Oh, hello everyone. It's a great pleasure to continue this workshop with this presentation on reactive bulk composition and Bingo-Antidote. I think that might be the most biased presentation of the entire workshop because I have been part with Eric Duersdorf of the development of this tool, Bingo-Antidote. So my objectives for this lecture are to discuss the concept of reactive bulk composition and explain why it matters for some specific cases when you use forward models. I want to present a selection of strategies that are viable to approximate to try to evaluate this reactive bulk composition. And then I will introduce you an alternative modeling strategy for thermobarometry that is based on what we call iterative thermodynamic models. And the follow-up is the program Bingo-Antidote that is running those iterative thermodynamic models. So let's start with a few basic definitions just to remind the concepts on which the models are based. We mentioned several times over the presentations that when we run the forward models, we assume chemical equilibrium. And this means that all the mineral phases in our system are homogeneous in composition. There is no compositional zoning, and they coexist in equilibrium at the pressure and temperature conditions of interest. Now, if we have a reaction, so for example, if we change the pressure and temperature of the rock, the path by which a rock will approach the next equilibrium state, it involves kinetic processes such as dissolution, here for a given reaction on this sketch on the right, transport, precipitation processes, and diffusion in the minerals to re-equilibrate their composition. Those are kinetic processes, and to apply an equilibrium model to the rocks, we assume that a set of local reactions proceeding in different microscopic domain will add up on some rock scale to give a balanced metamorphic reaction. And here what is shown here is a grain. I want to describe the grain boundary equilibrium model that if the transport in the intergranular medium is fast enough, if it's faster than the rate of dissolution and precipitation, then the composition of all crystallizing phases will be identical everywhere spatially and only dictated by pressure temperature and the bulk rock composition in case of equilibrium. And this is something we can test. We can test if the composition of the phases is crystallizing at one time is the same everywhere. I will show you a few examples to start, and those are all examples of garnet. And I selected the first case here, where the garnet formed, or the rock, the peak temperature for the rock is 550 degrees. It's garnet in eclogite. You have two compositional maps. The one on the left is the map of calcium in atom per formula unit. The one on the right is the XMG. And what you can see is that we have a succession of growth zones in this garnet, and at the scale of the thin section, we are almost looking at the scale of a thin section. The succession of composition is identical in all the grains for calcium and also for X magnesium. So which means that during the growth of this garnet, the grain boundary equilibrium model was probably satisfactory. The same composition was crystallizing at every location at the thin section scale. So I put it close for the grain boundary equilibrium condition, probably close. Those grains, they didn't re-equilibrate by diffusion. You can see that we preserve the compositional zoning. It's a bit more, it's sharp with calcium, it's less sharp for iron and magnesium. So probably we have a bit of diffusion in this case. But the re-equilibration by diffusion is limited, so we can use this composition to estimate pressure and temperature condition of growth of the garnet. But it means that this rock didn't reach a global equilibrium at the peak conditions. So we cannot apparently use the bulk rock composition to model the entire PT path of this rock, because we have a fractionation effect in the garnet. The second example is a garnet in granulite, and the Tmax is now higher. We are at 850 degrees. And I showed you again two maps. It's exactly the same scale as in the previous example. Here we have 2 millimeter, and we are looking at calcium again on the left and XMG on the right. And what you can see is that in this example, the mineral composition, the garnet composition, is quite homogeneous. There are some minor variations, but those are really minor. So we can't really say if a grain-boundary equilibrium model was at play during prograde metamorphism. For sure, we had reequilibration by diffusion, so we are probably close to completely reequilibrate the garnet composition. And it means that we might have a global equilibrium at the scale of the sample at the peak conditions. So we might be able to use the bulk rock composition to model this sample. And now I have a third case, and we are looking again at the size of its section, and you have an optical image of this sample on the left, and an X-ray compositional map on the right. This is X-Pyrope. It's an high pressure metasediments from the Alps, and the peak temperature is about 780 degrees. And what you can see is we have a different composition of garnet depending on the area in the thin section. So top left, we have a moderate X-Pyrope values. Then we have low X-Pyrope values in the narrow region. And on the bottom right, we have high X-Pyrope values. So in this case, it means we don't know about the grain-boundary equilibrium condition during prograde metamorphism. We had reequilibration by diffusion, but it follows a complex pattern with different local compositions. And for sure, the global equilibrium at the peak was not achieved. Maybe a local equilibrium was achieved in this case. But for sure, the preserved garnet composition does not reflect large-scale chemical equilibrium. I mean, large scale at the sample scale in this example. Of course, those are a very simple example. You will see one case, one more extreme case in the talk of Dave Pattison on kinetic tomorrow. So in the end, if we think about it's a complex problem, because the equilibration volume, that is the volume over which an element, a given element, is equilibrated, will depend, or the size of this volume will depend on the diffusivity of the element. Here I showed you an example with two elements, a low diffusivity element in dark gray and a high diffusivity element in light gray, and you can see the equilibration volumes will be different. So what we do when we want to run a thermodynamic model, a forward model, is we have to assume that for a local equilibration volume that is shown here on this figure in transparency, you have all the elements that you consider in your model that are equilibrated across this volume. So you can reduce the size of this volume to the element with the lowest diffusivity. And you can also extract, for example, the interior of the garnet if this one is not re-equilibrated by diffusion for the stage that you try to model. So that's the local equilibration volume, and the composition of this volume will be called the reactive bulk composition. So this reactive bulk composition, also known as effective bulk composition, I prefer the term reactive because it's really the part of the rock that is reactive at the stage that you try to model. This is a term for a model. It's the composition of the presumed equilibration volume at specific stage, at a specific stage of the PT evolution. It may exclude the interior of some grain, refractory inert minerals that are observed in the domain, but shielded from the reactions. And this reactive bulk composition is a conceptual quantity that we use as an input for the model. On the other side, you have two quantities, the bulk rock composition, that is something that you can measure. It's a measured quantity, and you can measure it, for example, by XRF. We can also use a local bulk composition. I will use the abbreviation LBC in this presentation. And this will be the average chemical composition of a specific region or domain in a rock. But this, again, is a measured quantity. And my talk is about how do we measure precisely a local bulk composition, and can we use a local bulk composition as an approximation of a reactive bulk composition? So how do we link the measured quantity with the conceptual quantity we use in the model? So to To measure, a simple approach to determine the local bulk composition, as Dave already mentioned, is to combine the mineral modes that you can obtain from backscatter images or from X-ray maps with the mineral compositions that you can determine using the electron microprobe. Here is an example of a few mineral composition expressed in weight % of oxide, and you can combine those compositions directly to calculate local bulk composition. So, for example, for one element, silicon, the local bulk composition is the weight fraction of phase 1 multiplied by the silica oxide weight % of phase 1 plus, and you do the same for all the phases. But weight fraction is not really convenient because what we observe is a surface fraction that we try to make it equivalent to a volume fraction. So if you want to go from the weight fraction to the volume fraction, then you need to add the density term, and it's simply the weight fraction of a phase is equal to volume fraction multiplied by the density of the phase divided by the density of the mixture or the density of the rock or the domain that you consider. And if we generalize this equation, by knowing the volume fraction of each phase, the composition of each phase in weight % of oxide, then we can calculate the local bulk composition. But there are some limits if this estimate is based on backscatter images, for example, because you have minerals with different composition that cannot be distinguished from each other. And the mineral zoning that can be important is not always visible in backscatter images. If you have, for example, a core on the rim of a garnet, you could imagine to separate this garnet into 2 phases. So a more general and flexible approach would be to use quantitative compositional maps. And this is an example of a phase map. So each color is showing a mineral. And for each pixel, we have a full mineral analysis. So we know the chemistry of each pixel. So we can use exactly the same approach. We can use the volume fraction of each pixel, the density of the pixel divided by the density of the area that we select. And by doing this sum, we can recalculate a local bulk composition. It's very straightforward. And then if you do that, you can apply, you can use any area on your map to extract a local bulk composition. This will be the local bulk composition number 1. And this is an example of a larger area that will be local bulk composition number 2. And then you can use that as an input in your model. We can also estimate an uncertainty because, of course, if everyone here would select on this map, that is another example, an area, a quite large area of interest, then you might end up with small differences. And we can simulate that by using a Monte Carlo simulation. And in this case, what I did is I just drew a rectangle, and then I used an algorithm to move randomly each corner of the area, which means that you can extract 2000 local bulk compositions that are slightly different domains for these syntactions. That's the summary. You obtain a mean value. That's your local bulk composition. That is very similar for this example to the bulk rock composition. You have a standard deviation, and you can extract an uncertainty. And then it becomes very straightforward and quite easy to propagate this to the forward model, to the Gibbs energy minimization. You can simply take the 2000 local bulk composition that you obtain, and you call 2000 times the Gibbs energy minimizer, and you look at how the results are changing. In this example, I did that at 425 degrees, 1.3 GPa. And then I showed you just 2 results. The first one on the top is the modeled mineral modes for fungi, and that would be the effect of the uncertainty on the local bulk composition. The mode is 21.17 volume % plus minus 0.13 at 2 sigma range. You can also quantify the effect on the model mineral composition. This is an example for silicon in atom per formula unit of fungi. The result would be in the model 3.48 plus minus 0.002 atom per formula unit, again at 2 sigma, which means that in this case, the uncertainty on your local bulk composition has very little effect on the position of the isoplates in your phase diagram, especially in this case, tested only on one pressure and temperature condition. But for that, you need to obtain a quantitative compositional maps if you want to use this strategy. What you measure at the electron microprobe are X-ray maps. Here is an example of a map of silicon, K alpha, it's the unit is X-ray count, and you want to transform that into a map of SiO2 in a weight % of oxide. So this is a standardization. And then if you do that, you could eventually calculate a map of structural formula. And as Matt Cohn nicely put it in a paper in 2000 or 2001, with this method, you can measure, you can really quantify the compositional variability of your mineral phases at the scale of the thin section. And actually, we do that much more precisely that we can model those mineral compositions. I developed a program if you want to do that quite easily, and it's now known as XMAP tools. And I will give you much more details on the Friday's discussion topic on XMAP tools. But basically, it can do all the transformations for you. If you have a few spot analysis on the same area, you can calibrate your maps. You can determine the phase proportions in any domain. You can calculate local bulk composition, and you can visualize the result like maps of structural formula. So after this introduction, I will move forward to the first topic of this presentation, that is this quantity, the reactive bulk composition. How do we approximate this reactive bulk composition? And I put it here a very simple sketch of metamorphism, that is the progressive transformation of the crustal material upon increasing pressure and temperature. And I put this sketch because what you can see on this sketch is a first effect that our reactive bulk composition will come into play, how you will change the original bulk rock composition of the system. And those are the fractionation effects. The first fractionation effect is to remove component out of your system. For example, if you extract an aqueous fluid that is produced by a dehydration reaction, then you fractionate H2O out of your system. If you extract a melt at higher pressure and temperature conditions, then you will again fractionate the composition of your system. But that's one way. You have a second way, that if you crystallize minerals in your system that will preserve their original composition, so if they are zoned, they will also fractionate the reactive, the composition of the reactive part of the rock will change during metamorphism. So, and we have modeling tools for those two types of fractionations. The first is fractionation by extracting components from the system, such as aqueous fluids or melt. And we have seen already yesterday during the presentations that you can do that in Taiyak Domino. You can run that in Perplex as well. And you can do that in Thermocalc. If you want to have some examples of applications of extraction of melt with Thermocalc, I encourage you to take a look at the papers from Chris Yakinchuk, for example. But those are the basic tools, and you will have to do a lot of things a bit manually at some stage. There are some more advanced tools, and here I put just one reference to one of them, that is rCrust by Matthew Main. And I really encourage you to check this tool. If you're interested about processes occurring along a pressure temperature path in which the reactive bulk composition will evolve and will change, where you will, for example, inject melt or extract melt from your system, then you must give a try to rCrust. This is a very great tool, and it can produce this kind of modbox diagrams where you have extraction of melt during a metamorphism. The second type of fractionation I mentioned is the isolation of components in your system when you grow minerals. This is a typical example of garnet zoning in manganese. Here I'm showing you a map with the X spessartine, and you see that we have this bell-shaped profile zoning in this garnet, which means that you progressively fractionate components from the matrix when you crystallize this garnet. And as you do not re-equilibrate this garnet during metamorphism, you will fractionate and change the reactive bulk composition. And we came up with a few figures in a recent review with Martin Ingi, and we calculated that if you have a porphyroblast, a garnet porphyroblast that represent more than 2 volume percent in a pellitic system or more than 4 volume percent in mafic system, then you might want to consider fractionation effects because they can become important. It's also important to mention at this stage that the processes of diffusion, resorption and replacement will work against fractionation. So they will tend your reactive bulk to come back close to the bulk rock composition in this case, in case of internal fractionation. And those effects of garnet fractionation, they are known since a very long time. For example, if you come back to the paper of Speer in 1988, you will see that he already quantified how garnet fractionation will affect the position of the isoplates in a PT diagram. But it remains neglected or ignored in some of the modern petrological studies. I want to show you one example why it might be important to consider garnet fractionation. This is a very classic example from Matthias Schmolke. And what he did, he considered an ecloguide and he modeled the garnet crystallization along a PT path that is shown here in this PT diagram. So the garnet becomes to be stable at this stage here. And he divided the PT path into 100 steps. And he ran two different models, one model along the 100 step where there is no garnet fractionation, and that would be the composition of the garnet end member that is predicted to be stable during the growth of the garnet. And a second model in which there is garnet fractionation. And in this case, what you can see first is that the composition of zoning in garnet, look at, for example, pyrope and grossular here, is different between the two scenarios, because in the step in the case on the right, the reactive bulk composition is changing along every point of the PT path. In this case, the bulk composition is used for every point. The second point that is important is that in the case where you consider garnet fractionation, garnet will stop to grow at stage number 50, which is here in the PT diagram. It's about 2.5 GPa and 600 degrees. And that's the maximum pressure that we have in most of the ecloguides that we collect in the field from the subduction zones. So it's quite interesting to notice that if you do not consider garnet fractionation, you might grow garnet up to ultra high pressure conditions. If you consider garnet fractionation, garnet might not record the peak pressure conditions. It also affects the fraction of garnet that you model in your model. If you use, for example, an equilibrium model, you will overestimate the amount of the model abundance of garnet in your system compared to if you use a fractional crystallization model. And we did that for exactly the same case as Matthias Schmolke. How do we fractionate? How do we calculate this fractionation? There are several approaches that are available. You can assume a Rayleigh fractionation of manganese between the garnet and the matrix. And then if you assume the KD and you know the amount of garnet in your system and the bulk manganese content, you can calculate the composition of the manganese depending on the amount of garnet that you have formed in your system. You can also progressively update the reactive bulk composition at each stage. And this is exactly what Matthias Schmolke has done with Thermodynamic Model in the paper I just showed before. If you want to model the garnet growth along different PT trajectories, you have several tools that are available. And I really encourage you to check those the tools that are available. For example, Teriac, that is distributed with Teriac Domino. This is from Fred Gades. And you can fix the PT trajectory and it will model how the garnet grows along this trajectory, and it will also consider diffusion. If you don't know the PT trajectory, if you want to do thermobarometry, then I really recommend you to take a look at this paper from Moyan and Pattison. This is an amazing work because it shows that you can use an iterative optimization, and for every microprobe analysis that you have along your profile, from the core of the garnet to the rim of the garnet, they optimize the pressure and temperature condition in order that the observed garnet composition will match the model garnet composition. And here you can see it, but along the profile, you have the dot for the measured garnet composition and the dots for the model garnet composition, which means that it's to me, to my knowledge, the best fit we have for garnet with a model that is based on equilibrium thermodynamics. And this is pretty amazing. You can go one step further and you can try to make the model a bit more complicated. And we tried that in 2017 with some co-author, and we produced a program known as GRT mode. So we do something similar that for each stage of a garnet, so for which composition that we have, we can model the optimal pressure and temperature condition by trying to minimize the misfit. And the misfit would be the difference between the measured garnet composition and the model garnet composition using some weighting parameters. And weight in this case are very important. So you can find the optimal PT conditions for the core of your garnet, and then for the second stage, when you grow the first rim, the model can also resorb the previous garnet that was formed, which means that the parameters that are optimized are pressure, temperature, and resorption of the previous growth zone, which means that the reactive bulk composition is optimized at each stage of the model. And I'm going to show you very quickly an example of this. And this is a very complex garnet texture from the Cesia zone. It's high pressure, low temperature garnet. And I have here maps of X grossular, X almodine, and X pyrop. And then I have a summary of the three main compositional groups of garnet that we have in this sample. We have a core here that is a Permian. It's a high temperature, low pressure condition core. And then you have two rims shown in gray, the light gray and white, that are the alpine overgrowth. So it's much younger metamorphism and it's high pressure, low temperature. So you can take three compositions that are representative of each rim. And then the program will optimize the growth condition for each stage. This is stage 1, the high temperature, low pressure conditions. Stage 2 at high pressure, lower temperature, and stage 3. But the most important is not in this case the PT, but what the program will predict for the garnet growth and resorption history. So you first, during stage 1, grow a garnet 1. This is the core of the garnet here. And then you have some moderate resorption before the crystallized garnet 2. And the most interesting part is at the third stage, where you have dissolution of garnet 2, precipitation of garnet 3, and a bit of dissolution of garnet 1 that is predicted as well. And the total amount of garnet is not changing that much. And this is exactly what the texture is telling you. You see that you have a replacement of garnet 2 in gray by garnet 3, and you also have some dissolution of the core here during the formation of garnet 3. So you see that you can model very complex garnet texture if you use a reactive bulk composition. So this was an iterative thermodynamic model, but it was a very simple iterative thermodynamic model in which I only compare the garnet composition from my observations, from my compositional maps, with the mineral composition of garnet that is predicted by a 4-1 model. And we can bring now this one step further by considering all the outcomes of the model, the mineral assemblage, the mineral modes that are the volume fraction of the phases, and all the mineral compositions that are predicted by the 4-1 model. And we can compare this with the observations that we extract from the rocks. But the problem is that if you want to apply that to natural rock, you can't really use the bulk rock composition. And the reason is very simple. When you use a bulk rock composition in your model as the input of the Gibbs energy minimization, this bulk rock composition comes from rock powders, so that you extracted of a part of your sample that you crush and you make a rock powder and you analyze by XRD. The observations on the other side, they come from a different part of the rock, a different volume. And this is usually a thin section from which you can extract the mineral assemblage, the volume fraction of your minerals, and the mineral compositions by analysis at the electron microprobe. So the comparison that you do is often partial, and you are considering things that are not exactly consistent because it doesn't come from the same volume of rock. So one alternative strategy that we use for iterative thermodynamic models is to use compositional maps here of a thin section. And then from the same area of interest in your map, you can extract a local bulk composition. And from exactly the same surface, exactly the same volume, you can extract a mineral assemblage, a mineral mode, and the mineral compositions. And if you have all those information, then you can run an iterative thermodynamic model. You just need to put the bulk composition as an input here in the 4-1 model, for example, using Tire Domino or using Perplex. And then you predict for any pressure and temperature, the mineral assemblage, the mineral modes, and the mineral composition. And you compare those outcomes with all the observations that you extracted from your domain on the thin section. You can calculate a misfit parameter that will quantify the differences between the observation and the outcome of the model. And if you try to minimize this misfit parameter to make them match, you can optimize pressure and temperature conditions. And that's the core of the strategy of those iterative thermodynamic models. So yeah, but there are a few problems on the way, because if you want to do this comparison between observation and outcomes of your model, you need to calculate this misfit parameter. And it's quite a complex story if you really try to do that, because there are many, many parameters with their own uncertainties. So we thought about it for several years with Eric Dursdorf, and we came with a scoring strategy that is based on what we call model quality factors. And that's the Q parameters that I will present now. So those are model quality factors, and they quantify how good the observations and the outcome, if they are identical or if they are different. So you have three types of observations and model outcomes. So we decided to go for three different model quality factors: the QASM for the assemblage, the Q volume for the mineral modes, and the QCMP for the mineral compositions. And those model quality factors, they have values ranging between 0, it means that observation outcomes are completely different, or 100%, where they are identical within uncertainty. So you can combine those three independent model quality factors into a dependent one that will be the Q total that combines all of those values. And then you can use this Q total as a misfit parameter. So you can run the inversion of your problem. But for that, we need to estimate those values of QASM, Q volume, and QCMP. And I'm going to show you an example of what does it mean, those values of those model quality factors. This is the first example for QASM. We have two different columns here. Teriac, this is the model. XMAP, that would be the observation. And if we have phases ABC in the model, phases ABC in XMAP, then we will have a model quality factor for QASM that is 100%. Now, if we have two phases in the observations that are not present in the model, the value of QASM will decrease. In this specific case, it will be 60%. For the Q volume, we will be looking at the modes, the volume fraction of the phases, again, in the model. That is a situation in the model for phases A, B, C. And on the right column, that would be for the observations on the map. And from this set of values, you can calculate a value for Q volume. And of course, the Q volume you can only calculate it if you have matching phases. If you have phases that you have, for example, in your observations and you don't have them in the model, then you can't really calculate how good or how bad they match. So you can only calculate Q volume for the matching phases. And then there is the mineral compositions, and we do exactly the same. So we have a complex equation that can calculate the value of QCMP for any mineral, depending on how good the model composition is compared to the observation. And I want to show you an example. If the value of QCMP is 100%, then it means that you have perfect match within the analytical uncertainty of your electron microprobe measurements. If you have a value of 80%, it means that you have some significant differences, usually greater than 10% in some key elements. For example, here I show you for Biotite, 4 elements: aluminum, iron, magnesium, and titanium. The first column is the observation with some analytical uncertainties expressed in atom per formula unit. And the second column would be the modeled composition. And the color code here is the same as for the color bar. So you see that for most elements, the match is very good within uncertainty. And for magnesium, there is a significant difference in the model compared to the observations. And that's why the value of the QCMP is lower. Now, if you take an example with, again, a lower value of QCMP, you realize that most of the elements, aluminum, iron, and magnesium, are badly modeled, and are significantly off compared to the observations. So that's how we estimate this value of the QCMP for each phase, and then we can sum them up to obtain a QCMP value for the model. How does that look in a PT example? So what I did in this example is I took an average P-light composition, calculated the pressure temperature phase diagram using this fixed bulk composition. And this is the results as it comes out of Teriac domino. And then I took the modeled mineral composition, mineral assemblage, and mineral modes at this PT condition, exactly 650 degrees and 0.8 GPa. And I took that as pseudo observations for a virtual rock. So that's where my rock is recalibrated. And then I calculated the maps of QASM, Q volume, and QCMP for the entire pressure and temperature region that is shown on this diagram. So the first diagram is for QASM, and you see the value is 100% in the stability field of the peak mineral assemblage. And this is good because it allows you to map the region where you have the best match between your observation and your model in terms of mineral assemblage. If you change one mineral, for example, if you add magnetite in the model, then you see that you have a value of QASM that will decrease, in this case, 85%. If you have minus storlite and plus a paragonite in this stability field, then you have a lower value of QASM. The second one is the Q volume. Again, the maximum is, the maximum value is 100% at the PT condition of the peak that we use in this example. And then we have a decrease all around, but you see that now we have less effect of the mineral boundaries. So for example, adding magnetite in the model here will not affect too much the volume fraction that in your model. The third one is for the mineral compositions. And you have to read this map that way. Here, what you see is a region where the value of QCMP is greater than 98, 99%. And this is the region where the intersection of all the isoplates of all your minerals are perfectly intersecting. So you can use those maps to read where is, at which PT condition is my modeled mineral composition perfectly matching my set of observations. The last step is to calculate the Q total. We have different equations in the paper. Basically, we use one where we weight all the parameters by QASM. So we multiply the Q volume by QASM. We multiply the QCMP by QASM, which would restrict the optimization within the stability field of the peak assemblage. And that's how you obtain the maximum value of Q total that in this example is at the 650 degrees and 0.8 GPa. But one of the questions that will immediately arise, and I'm sure many of you are already asking these kind of questions, is this saying, well, Pierre, you are using local bulk compositions, and I learned that I should use the bulk work composition. So does that matter? Does it matter if I use a local bulk composition instead of my bulk work composition, and what would be the effect of using a local bulk composition on my result, my pressure temperature result? Well, we can partially answer this question using the same example. So the same PT diagram, the same average metapelite composition, the same average pelite composition. And what I did is I ran again a Monte Carlo simulation, but a bit more complex than the one before. So I took the fixed mineral composition from the model at this PT. Okay, so the mineral compositions are fixed. And then I calculated variable modes, in this case, 10,000, that are simulated using a Monte Carlo simulation. And I just picked the bulk rock composition, that's the modes for the bulk rock composition. And then I have three different simulations. The first one shows a case where you would have a lot of garnet in your local bulk composition, in your local equilibrium volume. The second one, you would have a lot of plagioclase and very little garnet. The third one, you would have a lot of muscovite. And if you take an average grade metapelite, and you make a map of your metapelite, you will see exactly those three domains. One domain with more garnet, one domain with more plagioclase, and one domain with more muscovite and quartz. So this is really representing the variability of the modes that you have in one given sample. So if I multiply the variable modes by the fixed mineral composition, what I will obtain is 10,000 different local bulk composition that would represent 10,000 different local equilibration volume in my virtual metapelite in this case. And then I run two different scenarios, so two different simulations, always at fixed pressure and temperature conditions, so at these pressure and temperature conditions. In the equilibrium scenario, I take all the mineral compositions that are predicted to be stable here, all the minerals. And then I said, okay, let's try another case where we have a disequilibrium scenario. And in this case, I take the mineral composition from the model outcome at this condition as well, except from one phase. And I decided that the wrong phase would be plagioclase. And I took the composition of plagioclase at this PT condition. So I simulate the case where a prograde plagioclase will not be fully re-equilibrated at the peak conditions. So the composition of the plagioclase does not represent the peak conditions. So we have two different scenarios, and the question is, how are those local bulk composition affecting the outcome of the model at 650 degrees and open GPA? So let's start with the equilibrium scenario. I calculated the Q total value for all the models that I generated, 10,000. And I'm showing you the result in the space where we have the amount of plagioclase that we use to calculate the local bulk composition versus the amount of garnet. And the third dimension is the Q total. And as you can see here, for every simulation, we always obtain a value of Q total that is 100%, which means that the model will always perfectly match the observation, whatever the domain that you investigate. So put it with words, it says the investigation of a well-equilibrated sample can be performed using the bulk rock composition determined by XRF or any local bulk composition. You will always end up with a maximum value of Q total of 100% at these PT conditions, that are the peak conditions. The problem is that all the phase diagrams will be slightly different. And Dave Waters just showed us exactly the same with his previous talk. If you change the bulk composition, you change the geometry, as you move slightly the phase boundaries. But at the PT max condition, at the equilibrium conditions, all the models are identical. Now, if we take the disequilibrium scenario, I will shortly say a few things. It's exactly the same diagram, but we are looking for the z-axis on the QCMP values of the minerals. And remember, along this axis, we have more plagioclase with the wrong composition. It's the wrong composition of plagioclase for the peak conditions. So it's a metastable plagioclase. So you can guess it, if you have more of the wrong plagioclase composition, the model quality, the QCMP for plagioclase, will be low. And if you have less plagioclase, the QCMP for plagioclase will be higher. So you increase from 40% to 80% for the QCMP value. Now, if you change the composition of the plagioclase in the model, because you introduce this plagioclase with the wrong composition in your bulk constraint, then you will affect the garnet, because there is calcium partitioning between plagioclase and garnet. And if you affect the garnet, you will affect the iron magnesium partitioning between garnet and starlight. So the model quality factor of both garnet and starlight will be lower than 100%. So what we could say for this example is that if you use different domains on your thin section, one with a lot of plagioclase and one with few plagioclase, you might realize that something is changing in the quality factors of your model. And this means that maybe you will discover that plagioclase was probably not re-equilibrated at the peak condition. And that's exactly what we simulated here. So the third part of this presentation is about Bingo-Antidote, and I want to quickly show you an example, a quite simple example of how Bingo-Antidote works. And Bingo-Antidote is a program to run this kind of iterative thermodynamic models. And it's made of two parts. Bingo, the first part, that uses Teriac to minimize the Gibbs free energy for any set of pressure, temperature, and the local bulk composition. And then in the algorithm, the Bingo will compare the outcomes of the model with your observation, and it will evaluate the values of QASM, Q volume, and QCMP, as well as Q total. And then in Antidote, you have a series of optimization subroutines that can be used, for example, to determine the optimal pressure and temperature conditions. In this example, by trying to obtain a value of Q total that is as high as possible, ideally 100%. This is how the program looks like, and it can handle directly compositional maps. In this map, you can see that we have an area with the black lines here. That is a quite large area. And the program will immediately calculate the local bulk composition of this area and put it in the Teriac domino format. This is the input, the bulk composition of this area in the Teriac domino format. And then you have to do as well is you have to define some composition, reference composition for your phases. This is an example where I pick the composition of garnet, and I do that for all the phases I have in this domain. And then you can simply enter here in Bingo some pressure and temperature conditions, for example, 600 degrees and 10 kilobar. You hit the button Bingo, and the program will compare your observation that are shown here on the left with what the model is predicting at your pressure and temperature conditions. Here you see that we have several problems. We have kyanite in the model, whereas we have sillimanite in the observations. We don't have muscovite. We have muscovite in the model, no muscovite in the observation. And the quartz, I'm using the Berman database. There is alpha quartz and beta quartz, and you see it's not the right quartz in the model. So of course you can play with bingo. You can increase temperature, decrease pressure. You might go to the sillimanite stability field and find the perfect match. Or you can select antidote, and the program will try to find the optimal conditions for you. And this is a real-time calculation with Bingo-Antidote. So the program starts by gridding, so by minimizing the Gibbs energy for any PT conditions, and it draws maps of Q total. This is minus Q total because we try to do a minimization, and you have the QASM, Q volume, and QCMP. And then from this point, the program will run an inversion and converge to the optimal pressure and temperature for this specific case. And here the result is 733 degrees and 0.7 GPa. You have the values here of the Q parameter, the QASM 100%, Q volume 98%, and the QCMP, that is 90% in this example. So the Q total is 96%. And you see you have a perfect match between your observations and the model for those conditions. And the tables below will show you the composition of your phases in the observation and in the model. But I want to quickly go through the output of Bingo-Antidote for this specific run. And that's what you obtain in the output. You have your bulk composition that was used, you have the database that was used, the optimal temperature and pressure conditions, and then you have the evaluation of the assemblage for all the phases that are present in the model, in TERIAC, in the model, and the X maps in your observation. And the one simply means that the phase is present, and QASM is 100%. Then you have the evaluation of the volume fraction. So you see the volume fraction in the model on the first row, in your observations on the second row. Those are the absolute differences in volume fraction. We have just minor differences, for example, for Biotite in this example. But that will be the value of the optimal value for the Q volume, 98.5%. And then you get a detailed comparison of the mineral composition. And I showed you two examples for this case. Garnet first, where you have the model composition on the first row for calcium, magnesium, iron. And this is a manganese-free system. That's why you have a star here. And for the observations on the second row, we have some uncertainties for the observation. And then we calculate the model quality factor. This is 96% for garnet. It's almost identical within uncertainty. For the biotite, the situation is more complicated because the model in this database is very limited. So you can't really model the composition of the biotite that you observe. And the model quality factor is the QCMP value for biotite is pretty low here at 23%. And you see that the differences are significant in silicon, aluminum, iron, and magnesium. The last part of the output, you have the different model quality factor for each phase, and then it's combined into this QCMP value for the model. You obtain the chemical potential of the components that are modeled by TERIAC, as well as the volume fraction of the solid phases, the density, and you would have another output if you have a fluid that can be an aqueous fluid or a melt with the volume fraction and the density of your fluid. This is a list of all the subroutines that are present into Antidote, and I don't want to give you a detailed description of each capability of the program, but basically you can find the optimal pressure temperature condition. That's exactly what I showed you before. You can calculate PT maps of model quality factors using this recipe. You can calculate some PT uncertainty. So we have a search routine that will evaluate the shape of the objective function. So you can say, for example, if I take a threshold at 95% of my model quality factor, the program will map this line on your PT diagram. Then you have some single phase thermobarometry. What are the optimal PT conditions for my garnet? And the program will run a PT optimization for your phase. You can map as well the model quality factors. And then we have some sensitivity tests on the results of the Gibbs free energy minimization. We can, for example, vary the bulk, the input of the local bulk composition. That's exactly what I showed you at the beginning. The program will move each corner of your area and simulate that and see what are the consequences in the Gibbs energy minimization. You can do the same with the PT sensitivity, and you can combine them to do PT plus bulk sensitivity. We have some textual investigation tool. I will talk about that in a minute. And we can optimize some compositional variables and activity variables. For example, the amount of hydrogen in your bulk composition, the amount of carbon, or the amount of extra oxygen that you have in your bulk composition. That's variables that Antidote can optimize for you. Now I want to show you quickly an example. That's the example we provided in paper where we describe the program. It's based on a rock that Eric Djurstoff studied. It comes from Canada, and it's a metapelitic rock with garnet, biotite, sillimanite, staurolite, plagioclase plus quartz. I run a compositional map in Bern, and it's a quite large area again. The scale bar here is 2 millimeters, so it's half of the thin section that we mapped. And you see the distribution of the different phases. I showed you some compositional maps to show you that some of the phases are not zoned. For example, plagioclase, the composition is quite homogeneous here for the albite fraction. The garnet is quite homogeneous, even though we have some re-equilibration probably during retrogression at the rim of some of the fluoroblasts. It's another story for biotite, and here we are looking at the XMG in biotite. And you see that the distribution is quite complicated. It changes around the garnet, exactly where we have this high almandine content in the garnet. But if you go far away from the garnet porphyroblast, then you preserve probably XMG biotite that is maybe reflecting higher pressure and temperature conditions. You can easily also calculate maps or pressure temperature maps. This is an example of the temperature map in biotite using the calibration of Henry et al. 2005 that is based on the amount of titanium and the XMG. If you put that map into Bingo-Antidote, you select a large area of interest, and then you run the optimization, you will obtain optimal PT conditions for this sample using the June 92 database. This is from Berman with some updates from the Capitani, and you obtain condition at 671 degree, 0.6 for a GPA. And you see that you have a pretty good match between your observation and the model. We can have a look at the model quality factors. It's a bit lower for QCMP, but otherwise it's pretty good. And that would be the optimal solution. And that would be the uncertainty that is based on the mapping of the Q total function. So the optimal solution is here, 670 degrees, 0.65 GPA. Now, of course, you can extract the maps of the model quality factors. This is the map for plagioclase. Keep in mind that when the colors get in the red part, you have a perfect match of the mineral composition in the model with the observations. In this case, you see the plagioclase as an optimal solution here. Garnet would be a higher pressure and temperature. Biotite is not very high. The maximum value of QCMP is around 30%. And that would be the total map for QCMP at higher pressure and temperature. Of course, there is a strong effect on the solution model that you decide to select. And this is exactly why we selected this solution model with the bad model for biotite. So if you exchange the model of biotite and you go for a model that Eric Djurstoff produced that is compatible with the Berman database, then you increase the value here, the maximum value on the QCMP map of biotite to about 70%. Of course, we don't have MELT model in the Berman database, and it's no MELT model, so we can just run exactly the same exercise with the Holland and Powell database and the MELT model. And in this case, we obtain a pretty good batch for plagioclase, garnet, and biotite compositions at the PT conditions that are very close to what we estimated with the Berman database. So the peak conditions are identical with any database that you use, but the conditions of the mineral formations will be slightly different for this example. Now, if we can do some textual investigation. Here, for example, I have this window in red that can be moved over the area. So we calculated for 9 different regions the optimal PT condition back with the Berman database. And you might get some differences here in your PT diagram, depending on which region you analyze. And it's mostly dependent in this case on the amount of garnet that you have in your local bulk composition. So we could discuss about that. In the Berman database, the garnet isolates are at higher pressure and temperatures. That's why when you have more garnet in your reactive bulk composition, you tend to go to higher pressure and temperature conditions. So that was the presentation of Bingo-Antidote. And I'm now running out of time, so I will just quickly make a summary of what we have seen. When you run a phase diagram, when you calculate a phase diagram for the bulk rock composition, you basically restrict yourself to this colored map here on this diagram. So the temperature and pressure region, assuming equilibrium, assuming that equilibrium thermodynamic was achieved for the system that is represented by your bulk rock composition. If you have mineral composition zoning, if you have a fractionation of components from the system, then you might enter into the disequilibrium world that is shown on this slide of the diagram. And when you do some tests, so for example, when you extract the core of the garnet and you recalculate your phase diagram, you enter this world. When you play with Bingo-Antidote, you also, to some extent, you can explore part of this volume here. And there are some challenges, and partial reequilibration is one of the main challenges that remains, in my opinion, in when you want to model your rocks, the natural rocks. And I took here an example that it's a compilation of maps that we obtained for plagioclase. And what it shows you is that plagioclase is often in a disequilibrium scenario, as used in my Monte Carlo simulation. This is an example from the Central Alps. Tmax is 620 degrees. And in this case, there is a minor composition zoning of plagioclase, but what we demonstrated is that 80% of the plagioclase here with the orange composition was not reequilibrated at the Tmax condition. So 80% of the plagioclase was metastable at the maximum temperature condition. This is a second example from the Central Alps. Tmax is a bit higher, 680 degrees. And you can see from this image about 30% of the plagioclase is not reequilibrated at the maximum condition. This is an extreme case with a granulite from Himalaya. The Tmax is 820 degrees. And in this case, we conclude that 100% of the plagioclase was not reequilibrated at the peak conditions. And this would affect the isoplates of the other phases. For example, if you do not fractionate plagioclase, you might affect the isoplates of garnet, as I demonstrated in the Monte Carlo simulation. Plagioclase is not the only mineral that is often zoned. Garnet can be as well, white mica, epidote, amphibole, and so on. So I think it's important to realize that in this case, it might affect the phase diagram more than what we think. And this is my summary slide, where I think I tried to demonstrate that some fractionation effects are important, that they can affect isoplate thermobarometry. And if you are in one of these cases, you must want to use a reactive bulk composition instead of the bulk rock composition. The local bulk composition can be used when you want to investigate your rock for thermobarometry as a reactive bulk composition, and especially if you use iterative thermodynamic models. Then it is recommended to investigate several domains in a rock that are potentially affected by partial reequilibration at the peak condition, because you can evaluate what will be the difference in the model quality between the different domains. And this might tell you if some of the minerals were not reequilibrated at the peak conditions. And then finally, based on iterative thermodynamic model, we can apply equilibrium thermodynamic in a much more, let's say, meaningful way for samples that show very complex pattern, like when you do not reequilibrate fully a sample at, for example, your peak conditions. And the perspective that I will send for the talk of Jacob tomorrow is, why don't we use those model quality factors to test the databases? Because we can easily compare the results of different databases, and we can test the specific solid solution models. So I'm going to take one more minute here to describe super quickly this map that shows you a pressure temperature map for one sample, where we have the different maps of model quality factors, QASM, Q volume, QCMP. Then we have the QCMP of garnet, the QCMP of plagioclase, the QCMP of K-feldspar, and the QCMP of biotite. And I calculated for exactly the same local bulk composition, the model with the June 92 database from Berman, the Spear, Pattison, and Cheney database, in which you have no melt models. Then I calculated for all the Orlando Powell database from TC551 of the original 2002 to the TC62 in 2000 with the white 2014 models. And you can evaluate from this map the differences between the solution models. And if we simply look at a few phases, for example, Garnet, you remember that in the red area, that would be the region where the observed Garnet composition is properly modeled within uncertainty. And you see that they are very comparable. They give very similar PT condition independent of the choice of the database. Even though there are some variabilities in the Orlando Powell databases, for example, lower pressure, then slightly higher pressure, slightly lower pressure, and slightly higher pressure again. It's the same for plagioclase. You would come up with very similar conclusion, and it is the same for K-feldspar. It's even surprising to say that all Berman database give identical solution as the most recent Orlando Powell database. But Biotite will never reach 100% in any case, which means that either Biotite, the composition of Biotite was changed by diffusion after crystallization, and we can't model it with the composition that we measured, or it means that the solution models are always not able to reproduce the Biotite composition that we observe. And that might be some inspiration to try to optimize in the future the solution models. But Jacob will do a much better job comparing many rocks and for different compositions, whereas here I'm only looking at one single rock system.
I'd like to thank Pierre for an extraordinary talk. Such an innovative approach. I think we witnessed the cutting edge of modern quantitative petrology. So thank you very much for that talk. We'll move now to the question and answer session. So we'll start with questions which would pertain to your talk, Pierre, and we'll see how those go as to where we have a break before we have the questions for you and Dave. So I invite Jacob to lead off.
Thanks, Dave. And yeah, no, thanks, Pierre, for a great talk. Every time I hear you talk about Bingo-Antidote, I get excited at the possibilities and what we can do with it. So I mean, actually, I had a question I wanted to ask you to start off here. So whenever we're, as metamorphic petrologists, deciding the bulk composition that we're going to calculate and use in our diagrams, there's some kind of bias. If we're doing XRF, you've got to decide which part of the rock you're going to crush up, and you know, there's assumptions that are made there. And the same in this, you know, local or reactive bulk composition approach that you've just talked about. You've got to, authors have some license to choose perhaps the modes and the compositions that they include, unless you're iteratively changing that with Bingo-Antidote. So my question is, what would you recommend to people when they're reporting these, how they calculated their bulk compositions? How can they be as transparent as possible with the choices that they make? So that we can make things reproducible and yeah, any suggestions there?
Yeah, it's a great question. There are several parts. The first one is, I mean, you have to explain how you obtain your reactive bulk composition. It can be a local bulk composition, it can be XRF. So the first thing is you have to explain how you obtain it and probably report the composition. And if you build it from mineral composition, it would be nice to report the data as well. So the mineral composition, the volume fraction, eventually the density that you use, but this is less important. For the first part of the question, it is complicated, and I would say it depends what you want to do. I have an extra slide, and this is just the result of the 4 simulation that I showed you, and with the very different modes, mineral modes. So if you use the bulk rock composition, if you use one of the simulation where you consider an area with a lot of garnet, or if you consider an area with a lot of plagioclase, or one with a lot of muscovite. So if you're interested about thermobarometry, and if the rock is in equilibrium, I would say it doesn't matter which one you use, because you should always end up to the same PT conditions. And this is because it's very simple. It's just because the Gibbs energy of your minerals is independent from the mode. So it would be identical in any case at one given pressure and temperature condition. But if you're interested in modeling, for example, the prograde reaction sequence, then the phase diagram would change. And this is something I haven't shown, and Dave already demonstrated that depending on how you select your local bulk composition, you will have a different phase diagram. And here you can see they are drastically different. For example, the garnetine reaction is here. When you have a few garnet, if you have a lot of garnet, then garnet will be stable through the entire PT space. But for the bulk rock composition, you have a garnetine reaction here. So I would say if you want to predict the mineral formation sequence, then you might go for the bulk rock composition, because that's the most likely if your rock was recalibrating through the prograde PT path. But if you are interested in PT conditions, then it doesn't matter which one you use, you should end up with the same answer.
Excellent. No, I think that's a really good explanation. I had a question that kind of links into that, asking about you're calculating these local bulk compositions from 2D data and sampling bias, which I think you just addressed in that whichever part of the thin section you choose, if you're looking at peak, you should hopefully get the same. An interesting comment about what about 3D variability in mineral shape? If you've got strongly anisotropic minerals, how that would that affect it in the same way? I don't know. Are there any tests on that?
It would be exactly the same. So you would have variations, of course, in your local bulk composition. So that's something we can easily test by comparing. For example, if you map a large area on your thin section, we say in one of the paper you should have more than 10 times the size, the average size of the average grain size. Then if you map large enough, you get very close to the bulk rock composition. You can't really, they are almost identical. But again, it comes back to the same question. Does that matter? Does it really matter if you underestimate one mineral composition? If you're interested about thermobarometry, it doesn't matter. You can take 25% of garnet. You could take an example with 80% of garnet. You would end up exactly the same pressure and temperature condition in a case of an equilibrium scenario where you are only interested in the peak condition, the stage that you try to investigate.
So I had a question following on from that. You just said that you recommend 10 times the size of your grain size. Yeah. So when people are picking maps, they have to choose carefully the area that they're going to map. Is there a way that you can map multiple areas and combine it in XMAP tools? Is that possible, or do you have to do that outside of the program if you want higher resolution? And how does it deal with grain boundaries and things? That was an interest of mine.
Yeah, that's a great question, and I would say it's all a matter of scale. No? Of course, when you want to map a large area, you have a pixel size, so the distance between 2 points on this image that is quite large. I think for this specific case is it should be about 20 microns. So if you have a phase that is smaller than 20 microns, you would just not analyze this phase. Or statistically, you will have a few pixels with this phase composition, but very few on the overall map. So yes, it is a problem. Again, it is a problem because you might skip a phase, but that is very, very small. But in this case, the contribution to the model is also, to the local bulk composition will be very small. Yes, you can combine areas in XMAP tools. It is easy if you do that during the same analytical session, then it is straightforward. If you measure them several times, then it might be a bit more tricky because you have to combine different coordinate systems. So that might be a bit more of effort to get everything in there. But it's easy.
Yeah, no, that's really good to know you can do that. So could you comment, and you've mentioned some of these things, I think, in your talk and just now already, the relative benefits of point counting versus XMAP tools, and which one is the better strategy in your opinion?
I don't think it makes much difference, except if you have very zone minerals. So here you would have a problem, for example, for the pyroxene. The composition of pyroxene is changing significantly between the amphasite and the pyroxene in the seaplantite. So for this one with point counting, you would need to have quite a few, you would need to have quite a lot of microprobe analysis. And in the end, you need as much time as to get the map. So I would say it's easier, it's faster to go for the map. And I have to mention here, I will say it again on Friday, that if you take this example, if you have the maps and you want to go to the end, it's about 1 to 2 hours maximum data processing if you are already experienced with the technique. So, and we are trying to make it even faster. So it's much less effort that if you have to just do the data reduction for 200 or 300 spot analysis on the same area.
That's excellent. No, that's a really good point, Pierre. Somebody here asking about high-grade metapelites during partial melting. There's some uncertainty as to when does the melt start to be segregated from this migmatite. How well can we model this using the local bulk composition and fractionation approach?
Yeah, it's a tricky question. I don't have a slide for that. I have a few examples in mind. I will show a figure. I will show a nice map on that example on Friday. I would say the problem is it's always the same problem. You need to measure the composition of an area that you assume that the minerals in there were in equilibrium at one given stage, at one given PT stage of the evolution. And if you have retrograde reactions, such as, like, for example, in this case, the symplectite formation, then you will never manage to if you take a local bulk area, composition of this area, you will never manage to model the right proportion of garnet and amphasite, because part of the amphasite was stabilized into the symplectite. And so it's the same with the melt. If the system was not open, you can still run some models, but the comparison of the mode will be useless in this case, because simply the crystallization of the melt will bias the modes of the phase compared to the peak conditions.
Excellent. No, thanks. That's a great answer, Pierre. Okay, so have you made any comparisons between your calculated PTX conditions using the local reactive bulk composition versus a traditional whole rock XRF? And entwined with that, if so, when do the local PTX conditions converge towards the kind of the global conditions? And have you made comparisons between well equilibrated and poorly equilibrated samples?
Yes, we have done that. So, but I only have the example for the relative well equilibrated samples. That's the same example I showed you during the talk. And so what we did is we applied the inverse modeling. We used WinTwig to calculate the reactions between the end member, and we obtain the PT conditions here that are within the stability field. If you use the bulk rock composition measured by XRF, there will be those conditions. And of course, you will obtain identical conditions with Bingo-Antidote. You will obtain the same condition. If you have a small uncertainty, if you have a small difference in pressure, this is likely caused by some problems, for example, in your assumption, or uncertainties that are not taken into consideration here when we plot the reactions. But they have to be very close from each other if the sample is well equilibrated. If the sample is not well equilibrated, I have a nice figure for that, but not in this presentation. I could find that after for the Q&A, the second one. No, it will be strongly different. And yes, it will be different. And in this case, the iterative thermodynamic modeling approach is, in my opinion, much more relevant, because you can really look at very small equilibration volume where you can reasonably assume that the phases were in equilibrium and that they preserved their composition of this equilibrium state. So I try to find this figure.
Okay, that's great. I'll ask you one more question, move to Bingo-Antidote, and then maybe we'll open up the Q&A and bring in Dave Waters. Somebody asking, does Bingo-Antidote require MATLAB?
Yes, at the moment, yes. We are trying to move away from MATLAB, but at the moment, yes, it does require MATLAB. There are several reasons behind this choice, but yes, it does. It's running on MATLAB at the moment.
And I'll ask you quickly, why is it called Bingo-Antidote again?
It's called Bingo-Antidote because it's an inverse of Tiriac domino. So you have Tiriac domino. In Tiriac domino, Tiriac is a I have to go to the definition of Tiriac domino. So Tiriac is a component that was used in a very long time ago to make a kind of medicine, no? And domino is a game, and Bingo-Antidote is the inverse approach of Tiriac domino. So bingo is a game, as is a domino, and antidote is what you produce with the Teriac. So that's the one of the reasons of the name. The second reason is when you get your result, when usually you get your reason, the first thing you say is bingo.